let's look at a graph problem, monsters. So what's going on here? We are in the labyrinth with some monsters, and we take steps, and every monster takes steps as well. And we want to get to an edge, right? We want to get out of the maze. So we don't want to get eaten or something. But we don't want to get caught by the monster. So if the monster lands in the same square as us after it takes its step, then we lose. So we want to know if there's some path that gets us out, and there's no risk of meeting up with the monster, right? So if the monster, if it's the best possible way to intersect our path, it still doesn't work. So in this example that we have, we can get out. We can't get to here, there's too many monsters in the way, but we can get to here just by running straight forward, even though this guy's like right behind us. So we go right, right, down, down, right, and now we're at the edge and we're out. Notice though that if this square were a dot instead of a wall, then we couldn't get out, because the monster, instead of chasing us, could run 1, 2, 3 to here, and we can only get there in 1, 2, 3, 4. So the monster can get there before us, and so we're trapped. We can't get out. Even if we were here instead of here, that would still be true, because if the monster lands on the same square as us, then we lose. So if we're both 3 away, that's not good enough. Right, we go here, he goes here, we would go here, he would go here, we would go here, he would go here, we would go here, he would go there, and then kill us. So anyway, this actually turns out to be extremely similar to the labyrinth problem from earlier. Right, it's the same, except the only question is how to handle the monsters. And the answer is that the monsters sort of look like walls in a funny way. And the reason for that is that we can never step on a square that the monsters can get to before us. Or at the same time as us. So that means that, right, so when we try to go on a new square, one way that we can't go on it is that it's a wall, in which case it's illegal, it's out of bounds, that's illegal too. But another way that we can't go on it is if a monster could have gotten there at the same time or earlier. And so we can just sort of pretend that it's a wall in that case, right? Because we know how long it took for us to get there. So we can know if a monster could have gotten there before or not. And other than that, it's the same solution as labyrinth, right? It's basically just a BFS. So this is actually going to be 2 BFSs. One BFS to figure out how long it would take any of the monsters to get to each square. And then another BFS using that information to figure out if we can get out or not. So let's do that. And we'll do it in Python. Monsters. So we have RC. Split. So we'll just read the lines. We'll definitely want to deck using BFSs. We will even put up BFS. No, it's a little bit, the second one's a little bit thin. I don't think it makes sense to do that. Okay, so the first BFS is for the monsters. And actually a trick that you can do to BFS on multiple locations at once, right, because there's multiple monsters and you want sort of the min of any of them, is you can just put multiple starting locations in at distance 0. And then actually everything will work itself out. We'll just put it in triples. So row, column, and distance. Yeah, so if you just put in a bunch of starting locations at 0, then you'll get the BFS will give you the minimum distance to any of the starting locations, which is exactly what we want. So that's a nice trick. And we also want to know A, I think, is us, right? Yep. Okay, and I think that's all we need. sort of handling the monster stuff. These will be the distances for all the monsters. So if we hadn't done that before, we'll do a usual grid handling. So the 4 directions. Maybe we'll do something a little bit different. So instead of sort of 2 parallel arrays, we'll just do one sort of triple. Let's see. Now I'm getting confused. These are the 4 directions. And I suppose we should check, if we're not going to check here, we should check here that it's actually in bounds. Not W, but hash for a wall. So if it's in bounds, and it's not a wall, and we haven't been here before, then we should do something. And I believe that's it, actually. It's kind of nice. And now we get our distance. But we'll just use the same queue. And similar condition. So either the monsters can't get there at all, or they take longer than this to get there. Then it's okay. Okay, so we want to get to an edge of the grid. And we're done. We need to find out the path. I'll do that later. Okay. We'll stop the program if we find out the path, and otherwise we lose. Let's just stop the program. Not in R, but in range R, in the lines we want to get in. Going to Q instead of M. Yes, in 5. Okay, well, that's a promising sign. I should have written here. Right. Okay. so we'll figure out the path to doing this. So this is up, this is right, this is down, and this is left. So if we move, we need to figure out what direction we move from the parent to get here. So that's what we're trying to compute with this for loop. This might be reverse. We did this as an array. Fine. Lowercase, right? Yeah, so we're going back and forth. The problem is that we're overwriting parent. We should only write parent once. Okay. R, D, D, R, R. Yeah, so this is actually reversed. It's hard to tell. And we don't need this print statement. R, D, R, R. Cool. I'm going to exceed it. Yeah, I'm probably not going to worry about that. Wrong answer, I will worry about though. Left. Yeah, we've done nothing move left. Right? Yep. Why not? gr is less than r. Okay. Let's try that again. Okay. So now we are passing, except for some time when it exceeds. And those, I think I will not worry about. Lots of monsters. I believe that we have a linear time solution. Right, you could imagine like a bad solution where you BFS from every monster. That would be too slow. Because each BFS takes like linear time in the size of the labyrinth or the maze or whatever it is supposed to be a labyrinth, sure. And there's a linear number of monsters, so that would be like n squared, and n is 1,000 times 1,000, so that would be like 10 to the 12, which would be too much. But we're just doing one BFS for all the monsters because of this trick where you add them all at 0. And so it should be fine. So I think this is just a case of Python being a bit slow, which is too bad, but you know, it's not a big deal. We got the concept. Yeah, so that's it. Kind of a neat problem. It's kind of neat that like it's still just more. It's just 2 BFSs, right? The monsters are sort of like pseudo walls, right? If you don't get to a square, you can imagine that the squares, instead of imagining the monsters, right? Imagine that the monsters are sort of like spreading. Maybe they're not monsters. It's like a goo, or, something that's spreading throughout the dungeon at the rate of 1 square. Because the monster, you sort of imagine that the monsters are going in all the directions, right? And so the squares are sort of turning into walls or disappearing or something as you go. And so that's what this ND array is for. It's sort of telling us when the square disappears, which we are checking here. Right. So in addition to checking if the square is a wall, you need to check whether or not it got disappeared or got overrun by monsters or however you want to think about it. And other than that, we just check if we're done. Extracting the path, as always, is a little bit annoying. The way I did it this time is follow the chain of parents, and then figure out what direction you would have gone from the parent to you. And you can add that to the path. And because we're walking the path from the end, this ends up, we have to reverse it. So that's the problem. Kind of a neat one.